Thank you for the very kind introduction and for the invitation. It's a pleasure to be here today to speak to you all about some of the research that I do and why I think it's so interesting. So as was said, the topic of the talk today will be the evolution, diversity, and habitability of planetary systems. So giving a rough outline of what I want to cover today. I will start off with a brief history of our own planets and how our views of the planets in our solar system evolved over the past few hundred years. And I'll touch upon the move to search for planets outside of our solar system, what we've discovered and what questions are still outstanding. And then I will try to convince you that young planetary systems are very interesting because they offer us a key to understanding the evolution, diversity, and potentially habitability of exoplanets. I should say I'm happy for this to be as informal as you all want. So if you have questions as we go, please do feel free to ask or wait to the end as you prefer. So this is an overview of our solar system. Got the sun in the center. We have our 4 rocky planets, Mercury, Venus, Earth, and Mars. These are the inner 4 planets in our solar system. And the outer 4 planets are larger gaseous planets, Jupiter, Saturn, Uranus, and Neptune. And there's quite a clear structure to the solar system. Rocky planets on the inside, larger gaseous planets on the outside. To give you a sense of the size of the solar system or the range between Mercury and Neptune, Mercury orbits the sun in about 88 days. Earth obviously orbits once every 365 days, or 65.25 days technically, I guess. And Neptune orbits once every 164 years. So there's quite a range in terms of orbital periods between our innermost planet and our outermost planet. Probably hasn't escaped your notice that Pluto is down here and is no longer considered a planet. And that's because as a result of the 2006 resolution from the International Astronomical Union, that there are 3 key things that a planet must be. So the first is it must be orbiting its parent star. Second is it must be gravitationally bound and in hydrostatic equilibrium. So essentially it needs to be an object that is roughly spherical in shape. And the third, and this is what tripped up Pluto, is that it needs to clear its neighborhood, its path in orbit around its parent star from other gas, dust, and planetesimals. And on that last one, Pluto hasn't completely cleared its orbit, and there are other objects that are in a kind of similar class, and that was what denoted Pluto, and sometimes referred to as Plutoids. It's a group of objects in the outer solar system. So our view of the solar system, the way we kind of think about it, has evolved quite considerably, from the original Earth being the center of the cosmos to in 1543, when the Polish astronomer Nicholas Copernicus put forward his, I won't even try to pronounce it, but the translation goes something along the lines of on the revolutions of the heavenly spheres. And in this idea, Copernicus put forward the idea that Earth was not the center of the cosmos, but actually it was a planet that orbited the sun, much like the other planets. And this really kickstarted a bit of an intellectual revolution, because if Earth was a planet, then maybe the other planets were like Earth. Maybe they had their own landscapes, their own moons, their own climate, and potentially their own inhabitants as well. This was taken one step further by Giordano Bruno, who said that if the sun is a star, then potentially the other stars that we see in the night sky are also suns, and they may have their own planetary systems that could also be habitable and indeed inhabited. Giordano Bruno was a Dominican friar and poet, philosopher, mathematician, who was put on trial in the Roman Inquisition for a variety of heretical views, mainly religiously heretical views, the least of which was his views on astronomy. So he was actually burnt at the burnt at the stake shortly after 1600, not because of his views on astronomy, but more his views on religion. 10 years after that, in 1610, Galileo put forth his idea of the heliocentric model versus the geocentric model. He put it forth in kind of a format of a play almost, where two characters were arguing the heliocentric versus geocentric sides of the argument, and the geocentric character was called at the time. It's usually referred to as what the idiots in plays were called. So it came out quite heavily in favor of the heliocentric model with the sun at the center and the planets in orbit. And indeed, the telescope observations of the lunar mountains and also the moons of Jupiter, then went on to be called the Galilean moons, provided pretty strong empirical evidence that the other planets in our solar system had some similar attributes to Earth. Mountains on the moon, moons around Jupiter, and so that the general kind of thought was that these planets could be like our own planet. They could be habitable and indeed inhabited. This was a kind of an idea that was kept for quite a long time. So a lot of the sort of nomenclature around the moon has the ideas that these larval basins, impact craters and larval basins, were actually seas. So they were thought to be a kind of water-rich surface on the moon, and that sort of held up until into sort of 1780s and beyond. So William Herschel, who discovered Uranus and also mapped out parts of the Milky Way, wrote to the Astronomer Royal at the time, Neville Maskelyne, and said essentially that it was very, very likely, if not almost certain, that there were inhabitants of some sort on the moon. And in his seminal work on, apologies, in his seminal work on Mars, on the polar caps of Mars, the atmosphere, and the polar axis, he finished off with an almost throwaway remark that its inhabitants probably enjoy a situation in many respects similar to ours. This was kind of commonly held view at the time. So shortly after that, it was kind of mentioned by Edmund Halley without any real controversy that Earth was a planet and other planets could be like Earth and indeed may be inhabited. So this idea that planets were habitable and habited held for quite a while until we started venturing out into the solar system. First with the Pioneer spacecraft and the Voyager missions. And this was one of the sort of famous sets of images sent back by Voyager 1 on its travels through the solar system. It was taken in 1990, and we have, going from top left to right, we've got an image of Venus, Earth, Jupiter, Neptune, Uranus, and Saturn. And all of a sudden, the idea of these planets as very habitable places was in kind of stark contrast to a very widely separated solar system with planets very far apart, with no obvious signs of life. And indeed, what kind of we began to know by this time that many of the conditions around on the surface of these planets wouldn't be conducive to life as we know it. And so we kind of transitioned from a very promising idea of the solar system to realizing that probably there's no clear signs of life at the moment. Potentially on Mars, microbial stuff, but in general, no clear signs of current life. And so this made us look out beyond the solar system, look for exoplanets. But this is a little harder in a way, because while in the solar system you can look at the planet and image it directly, when you're looking for planets around stars that are far away, even if there is a planet in front of the star or even around the star, all you see, because you're so far away from it, is just the glare from the host star. Very difficult, even with current technology, be able to image a planet anywhere close to its host star. The only ones we've imaged have been quite far away from the star. And so what we needed to do was to go to an indirect method of detecting planets. And there's an unlikely success story with this, actually. This came from now a famous system, 51 Pegasi b, which is the first exoplanet detected around a sun-like star. This was done using the radial velocity method. So this is illustrated here. So you have a star in the center, planet in orbit. So you get gravitational reflex motion of the planet induced on the star. And so the star wobbles towards and away from us. And we can measure that wobble, red shifted away from us and blue shifted when it's coming towards us. And we can map out the path that the star is moving in its orbit as the planet does one revolution around the star. This is exactly what Michel Mayor and Didier Queloz did in 1995, and this is the data that was presented on this system 51 PEG. So we have this nice radial velocity orbit in one revolution between phase 0 and phase 1. That's one orbital period of the planet. It does one sinusoidal revolution following this kind of orbit as the planet goes round the star. So it's an indirect method of detecting the planet, but there was no other good explanation for this kind of system. What was surprising, however, was that the planet was not really anything like what we expected. So in terms of its mass and its radius, it was pretty normal, about 1 Jupiter mass, 1.24 Jupiter radii, so a little larger than we might expect, but not unusual. What was unusual was that the distance to the host star was 0.05 AU, so it's 5% the distance between the Earth and the Sun. So it's 9 times closer than Mercury was to the Sun. Our own Jupiter orbits once every 12 years, whereas this planet orbited once every 4.2 days. Now, in our current understanding of how planets form, gas planets form far out in the disk, far out away from the star with long orbital periods. So it's quite a conundrum how you can get a Jupiter-like planet onto such a short 4-day orbital period. And I'll come back to that in a bit. This really kickstarted a bit of a revolution in the exoplanet field. We have a first detection in 1995, and then the number of detections increased year upon year. So this is the cumulative number of detections. So the jump from one year to another is the additional planets found in that year. You can see that the trend is increasing up and up and up, with a couple of jumps due to the Kepler space mission. The key point that I want you to take away from this plot is that while the radial velocity detections have been steadily increasing, it's really the transits that have hugely increased our number of confirmed and candidate exoplanets. And it's the transit method that I'll be focusing on during much of this talk. So the transit method is a really powerful way of determining the size of planets. So hopefully this will run. So it relies on the orbital inclination of the planet being aligned with our line of sight, such that when the planet goes around in its orbit, it passes between us and its host star. As it does so, it blocks out some of the light from the star, and you get a drop in the amount of flux observed from the star, just because some small fraction of it has been blocked out by the planet. And this will repeat each orbit. So it's a strictly periodic drop in flux for a few hours, separated by one orbit of the planet. The key thing to take away from the transit method is that it tells you about the relative sizes of the star and the planet. So here, if you have a reasonably normal sized star but a very small planet, you get a very shallow transit. And that's because the planet is only blocking out a very small fraction of the light from the star. Whereas if you have a larger planet, so the ratio of the radii between the planet and the star is smaller, so a larger planet to star ratio, you get a much deeper transit. And this one is the deepest of all the transits in the example, so it's the largest planet to star ratio. There's also some information you get about the shape of the transit. So if the planet is transiting near the edge or the limb of the star, you get a slightly more V-shaped transit. So from the shape of the transit data, you can tell something about the size of the planet, the orbital period of the planet, and what the orbital inclination is. The two key things are the size and the orbital period. Now, if we jump forwards and take a look at what we have discovered to date. So here we have this is the radius of the planets we've detected. This is against their orbital periods. So in green, we have planets that have been detected via transits. We have this population up here, which are pretty large planets on short orbital periods between about 1 and 10 days. These are our hot Jupiters. These are the systems that are very similar to 51 PEG. So a Jupiter-like planet on a very short orbital period. So in comparison, I put in here where Jupiter would lie if it was on this plot. So 12 orbital period, and about one Jupiter radius. So these are the same sized objects, but just much closer in. This is a log scale. So you go up by a factor of 10 between each one of these. We also plotted Earth and Neptune down here. And the key thing to take away is that all the planets we found around here, some of them are about the same size as the Earth, but they're all much closer in. Short orbital periods between less than 1 day out to about 20, 30 days here. And these objects, which seem to be kind of intermediate in size between Earth and Neptune, these objects seem to be quite numerous, although we don't have any such planets in our solar system. So the largest of the terrestrial planets, Earth, and the smallest of the gas giants, Neptune. There's no other planet in between those two sizes, but actually that seems to be quite a common planet size in other planetary systems. So taking the plot we just looked at and putting it into the form of a bar graph, this is showing the fraction of stars that have at least one planet of a certain type. The most common are these mini Neptune planets. These are planets that we think have a gaseous like Neptune, but is a little bit smaller. And the next most common are the super Earths. This ratio has changed ever so slightly now. But these are the two most common kinds of planets. Between Earth and Neptune, these super Earths and mini Neptunes. The good news is that Earth-like planets seem to be pretty common as well. Gas giants, like the hot Jupiters, like that we found with 51 PEG, they're easy to find, so we found them first, but they're actually not very common at all. So I mean, in terms of the relative occurrence rates of gas giant planets on short orbital periods that we are sensitive to detecting, the occurrence rate is actually quite low. This is now jumping into a different way of looking at the same information. So these are all planetary systems detected with the Kepler mission, the space satellite, the NASA space satellite. And each one of these objects that's going around in an orbit is a planet. And the time which it's going around is the orbital period. And you see the kind of the accelerated time here. But the key point that I want to sort of to show with this is, first of all, the variety of different systems you get. The sizes of the planets vary a lot. They're colored by the surface temperature, or the equilibrium planet temperature. And you see there's a wide variety in the temperature of these planets. But the other thing is that compared to the solar system, we have our 4 inner planets here, another one there, and we've got Jupiter out here. The scale of these other solar systems are much tighter. So something has moved these planets, we think, from where they formed further out in the planetary system, has moved them in closer to their host star. To illustrate one of these systems, it's a Kepler 11 system. against the scale of the solar system. So the two stars are reasonably similar, solar type stars. But the Kepler system has many planets within the orbit of Mercury. So our closest in planet, there would be 1, 2, 3, 4, 5 other planets closer in the orbit of Mercury. And it's not clear how they got there. We don't think, but we are not sure, that they formed in situ at that current location. We think they formed further out, and then they migrated inwards. So then the obvious question is, how? What were the processes by which they migrated in? And although we have theories, it's quite hard to test for the following reason. So in our current theory of planet formation, we think that planets form within the protoplanetary disks that surround young stars. And the further out in the disk, the lower the temperature. So the further from the star you are, the lower the temperature. Have sort of at a certain distance out what we call the snow line, where gases can condense into ices. And that material can be swept up in these forming planets, and that's what causes gas giants like Neptune or Jupiter, as opposed to predominantly rocky, smaller planets like Earth, Venus, Mars, etc. So one of the ways in which we can get these planets that we think formed far out in the disk in close towards their star is to migrate them through the disk. And there's a lot of active research going on about how planets can migrate through the disk while the disk is still there. The disk only lasts, we think, for an average about 3 million years. Some disks last as long as maybe up to 10 million years, but it's in astronomical timescales very short-lived. It's a very quick set of processes. Planet formation is quite fast. We actually think we observe potentially some signatures of planets forming far out in the disk. This is an HL tau system. So you have the star at the center, and then we've got a sort of not quite a face-on disk. This seems to be off by about 30 degrees or something to our line of sight. So we're watching it at a bit of an angle. But you can see these ring-like structures and gaps. And one of the hypotheses is that these are where planets are forming. It's a large gas giant planets that have swept out the material on their orbit. And at the beginning of the talk, I said one of the sort of defining things of a planet is that it clears its path in its orbit around its host star. And this is what we think we could be seeing. There are some other ideas that you can create these kinds of structures without planets, but at least one of the theories we have, the leading theories I'd say, is that these are formed by at least one and maybe more planets. So this is one way in which we can get planets to move in, interact with the disk, lose angular momentum, and then move in towards the host star. The other way is that you can form the planetary system with the disk. The disk then disperses, and you're left with an existing planetary system. And let's say you've got, in this example, 3 planets, reasonably far out, but the orbits are not completely stable. They gravitationally interact with each other. And what you can have is that over time, over about a few to several 100 million years, as indicated by this green band here, the system can become unstable, and what you get is one of the planets ejected, one of the planets sort of moved in on a highly eccentric orbit, so it loses angular momentum and comes in on a very highly eccentric orbit, very close to the host star. It tidally interacts with the star, and it loses energy from its orbit and circularizes into a very short period orbit, usually at about 0.05 AU, which is pretty much exactly where 51 Peg was found. So these two theories are both able to produce gas giant planets on short orbits, but which one is actually the right one? Or are both of them right? And if so, is it 50% of systems form one way, 50% the other way, 90-10? Where exactly is the balance? Which one is the dominant migration mechanism? The other way you can do with this scattering is not to have multiple planets in the system, but have a nearby star. You have essentially the same kind of interaction, gravitational interaction, excite the orbit of this planet, excite the eccentricity and its inclination, and then you can take energy from the orbit and circularize it on a much shorter orbit closer to the star. These are all viable options. If you're thinking, well, how can we not tell yet which way is the dominant mechanism? The reason is the ages of the planetary systems that we found so far, showing the age versus distance of transiting planet systems that we've detected, and you can see that most of them have an age of about 1 billion years or older. So these planets are too old and their ages are too uncertain to tell us whether they moved in onto their current orbits via dynamical migration, scattering of other planets or nearby stars, or if they migrated early and they migrated through the disk. So what we need to do is to find planets in this region of the diagram. And this is the key. This will allow us to link our theories of, apologies. This will allow us to link our theories of planet formation and protoplanetary disk evolution to this older exoplanet population. Skip that. Okay. And the way that we can do this is by looking at groups of young stars. So young stars form in a variety of environments. The main environments that they form in are large open clusters. They form in giant molecular clouds where you can get sort of tens to thousands of stars forming in the same star formation event over a period of a few million years, up to maybe 10 million years age spread within these clusters. So these are kind of groups of stars that form in the same location from the same parent material, and therefore you can study them together, and that is what allows us to determine the ages of these groups to a much higher precision than you can for any individual star on the sky. So when you have 1,000 stars together, you can use the ensemble nature of that system to determine its age, which you can't do very well for individual systems on their own, which is why these have such large uncertainties. So we are not alone in targeting these young open clusters and loose associations to find young transiting planets. So to date, we've got about 25 young transiting planet systems. We've detected around the nearest of these groups of young stars. And these are important because they allow us to determine which of these migration mechanisms seems to be important. For example, the planets we find here, this is 10 million years, just after the disk is dispersed. There hasn't really been time for this migration mechanism to kick in yet. So it's probably the more likely scenario that these young planets migrated through the disk rather than were scattered in by other planets or nearby stars. But these slightly older systems, they could have been formed either way. So the idea is we can build up a population and start testing how many of the young planets that we find kind of migrated through the disk and how many could have migrated through this dynamical interaction. This is perhaps easier said than done in a way. There's a very good reason why we haven't found as many planets around young stars as we have around old stars. And that's simply because it's harder. So this is a mock toy light curve of what a star like our sun would look like. Reasonably flat, a little bit of jitter, some small scale structure, but the brightness of the star remains pretty much constant. I put it in relative flux units. So a drop of 100% would take you down to 0, drop of 5% takes you down to about 0.95 here, drop of 1% takes you down to about here, 0.99. Let's imagine that there is a planet in this system, and let's imagine that it's transiting its star. So the star looks like this, nice and stable, not much going on, planet passes in front of it, and we get these nice periodic drops in flux as the planet transits in front of the star. that's great. We can see those transits, we can find them, we can see them by eye. We can definitely write a computer program that will be able to detect those transits in the data. That's quite straightforward. Young stars, however, are a little bit more interesting. They are the kind of teenagers of the star world. Lots of temper tantrums, lots of stuff going on. So young stars are more active. They have stronger magnetic fields. You can see that these dark regions, we call them star spots, just like the sunspots you see on the sun. But there are usually more of them in young stars. As these spots rotate into and out of view, so you imagine you have groups of several tens of spots all over the star. As these spots rotate into and out of view, you see more or less, or more or fewer star spots at any given time. So if you see fewer star spots, the star will overall appear brighter. You're just seeing more of the bright part of the star and less of the dark part of the star. And when you see more star spots, then the star will appear fainter because you see more of a higher fraction is darker because of the star spots. What this actually translates to is a light curve that looks something like this. So you have this sinusoidal modulation that evolves sometimes reasonably quickly. And this is when you've got, so here the star is appearing bright, so you're seeing fewer star spots. Down here is when the star is appearing fainter, and that's when you're seeing more star spots. And you also get flares of these stars, and the strongest flares are sometimes also eject material. We call them coronal mass ejections. In photometry, so this is just the brightness of the star as a function of time. These flares manifest as impulsive rises in flux, followed by exponential decays. So you can see these short-lived flares between these two. Now, the transits that I showed you before are still in this data, but they're just harder to find. So the fact that we haven't found many young planets yet, it's not clear whether that's because there are fewer young planets on short orbits, i.e. they haven't migrated yet, or they're there, but they're just harder to find, and we just have to work a little bit harder to detect them and then be able to characterize those systems. So one of the things we've been doing is to try and improve our methods to detect transits around variable stars. So this is actually a real light curve of a young star. And it's quite an interesting light curve, so I can use it as an example. The way that we had been detecting planet transits was to fit a model to the data. You typically use a model, it's a Gaussian process model, which you can think of as a way of parameterizing the covariance between pairs of flux measurements in your data, rather than trying to write down some kind of functional form of model, some combination of sines and cosines to fit your data. The key point is that it's a flexible model that can explain this evolving modulation pattern, but shouldn't be able to vary on very short timescales and eat up the transits. That's the key point. What we then normally do is look at the residuals of our model and then search for periodic structure. You can kind of see some periodic structure already going on in there. And so if we do that, we create what we call a periodogram. This is how strong are there signals at different periods. You can see actually there's a peak here, about 24 days. If we look at the data, you can see it corresponds to these times, which if we zoom in, we find some nice planet transits. So you can see that there's one there, one here, and one there. A bit of missing data, which is the beginning of that transit, but it's a genuine transit. So that gives us our first planet, quite a deep transit. But this idea that we had of doing this two-step process, fitting the data first, looking at the residuals, and then trying to search the residuals for transits is not the best way to do it. What if we try to do everything simultaneously? What if we try to model the variability at the same time as looking for periodic structure in the data. If we do that, we can create a far more interesting looking periodogram. See this peak here at 24 days again, but we see it stronger, which corresponds to this planet. But we also see these peaks. This is where things get quite interesting. So this peak corresponds to these times in the data. And then we pick up a second, much smaller planet. This peak corresponds to these times in the data. We pick up a third planet. It actually turns out that this peak is a combination of these two peaks because these planets are close to resonance, if I remember correctly. And then lastly, we pick up a single transit event right there in the center of the light curve, and that turns out to be the fourth and final planet in the system. So just by improving the method by which we detect planets, we went from detecting one planet in the system to detecting 4. So it does tell us that maybe these planets are there at young ages, we just haven't found them yet. But now that we have a better algorithm, perhaps we'll start finding more of them. So now that we have an algorithm, the next thing that we want to do is to know which stars we should be looking at. So which stars are young? So we go back to this plot I showed you before. We have these groups of stars. You said that the size of each of the circles tells you relatively how many stars are in that group, from tens to up to thousands. But we also want to know where they are in the sky. So this is a map, sort of a projection of the entire sky, sort of shown here. And then this orange line shows the path of the galaxy, the galactic plane. And we can see where young stars lie on the sky. So these are open clusters. You can see that they actually trace very nicely the plane of the galaxy, which makes sense because that's where there's a lot of gas and dust forming new stars. So it's unsurprising that these trace out the central plane of our galaxy. So looked at star forming regions. This is where you can start to see some nice kind of interesting structure. So these kind of box-like structures here, these are not real physical structures. These are just where people have looked. These are the footprints of where they've looked for young stars. So the young stars won't stop in this shape. There'll be more that we just won't know of because we haven't looked properly yet. There are also some very nearby stars. So these kind of very nearby groups, because they're very close to us, their members are spread all over the sky. So then we can see that there are lots of young stars spread everywhere in the sky, actually. And then recently, there's been a very nice piece of work looking for co-moving stars. These are groups of stars that all move together through the sky. And it looks actually increase your number of young stars quite significantly. So we know that there are lots of young stars now that we were struggling to identify before. We hopefully have a better algorithm. So can we actually find more planetary systems? That's the key. So the answer is hopefully yes. So this is the TESS, the Transiting Exoplanet Survey Satellite. So TESS has 4 cameras and is doing an all-sky survey satellite sent up by NASA. And the interesting thing about it is the way it is surveying the sky. So it's doing 27 days in each of these stairs. There's 4 cameras lining up one above the other. It's mapping out the southern hemisphere. And then it mapped out the northern hemisphere. And you can see that where these, there are some parts of the sky that get almost continuous coverage over an entire year. And so TESS is doing an all-sky survey. It's done, I'll just show that one more time. So it's done one complete survey of the southern sky, the northern sky, then the southern sky again. And it's now doing the northern sky one more time, including some of the gaps that you'll be able to see between the sectors. So in There's a little gap that wasn't covered in the first time. So TESS is the way that we're hoping to find lots of young planetary systems. And indeed, one of the systems that we found is this one. So this is showing almost two continuous years of data. So there's a 1 year of data here, another year of data. There's the brightness of the star as a function of time. So each of these vertical lines is actually one rotation period. But because there's a lot of time kind of squashed up into a short space, it just looks like vertical lines. But if you expanded it out, you would see that on each rotation of the star, you have this kind of like nice sinusoidal modulation. This is showing the rotation, the brightness variation over one rotation period of the star during the first year of observations, and then during its second year, which is actually 2 years later. And interestingly, you can see it goes from a nice sinusoidal modulation, where you've got one dominant spot group on the star, passing into and out of view once, to this one where you've got sort of probably two reasonably dominant spot groups. So you get almost like two cycles per rotation period from the front spot group and then the back spot group that comes into and out of view. Does anyone see any planets in that light curve? These are pretty hard to find. If we zoom in just on like a small 40-day section of the light curve, then you see something like this. The vertical blue and green lines tell us where the transits are in the light curve. But even when they're kind of highlighted and indicated where they are, they're still pretty hard to see. It turns out these are actually very shallow transits. The depth of the transit is about 1% of this variability amplitude. So it's quite a nice way that we found this system. It was quite a nice surprise, like kind of like so much so of a nice surprise that I had to kind of check and double check that I was happy that it was a real signal and not a mistake in some sense. So the things that we get, as I said, from the transits are the radius ratio. But if you know the size of the star you're looking at, then you can infer the radius of the planet. So these two planets are mini Neptunes. So they've got radii about 2.7 times the radius of the Earth, the inner planet, which is on a 4.7-day orbit, and about 2.9 Earth radii on an 8.8-day orbit. And so these are intermediate between Earth size and Neptune size. So Neptune, for reference, has a radius that's 3.8 Earth radii. So they're pretty much halfway between the two, slightly closer to Neptune in size. So great, we found some planet transits, reasonably confident that they are planets. But how do we know that the system is young? I mean, it's variable, so that's a good sign. But how do we know it's young, and how do we actually know its age? Rather than just say it's young, is it 1 million year, 10 million year, 100 million year? How can we determine that? And so the way we do it is to use, as I mentioned, these stars are members of groups. And so we can use the group nature to determine or help us constrain the age. And the way we do it is by two ways. First way is to look at the rotation period of the star. As it turns out, stars follow a characteristic evolution in terms of their rotation period. And so by comparing the rotation period for the star that we're interested in to lots of other stars that have age measurement, we can get a relative age diagnostic for our star of interest. So the cyan points here show stars that are about 100 million years old, and the magenta points show stars from a different group that are about 670 million years old. So the key point is that this is a color which is a proxy for mass. So you have high mass stars on the left-hand side here, low mass stars on the right-hand side. And stars that are here, for example, when they get older by about 500 million years, they should have moved up to there. These stars, when they get older by about 500 million years, they should move up to where these magenta ones. And These ones, when they get older, by 5 million years, they'll move up to where these ones are at the same color, or the same mass. And so then we can see where our star lies on this diagram, and also members of the same group, which is actually a reasonably well-studied group called the AB Doradus moving group. So if we do that, then we can see where our star and its group lies. And it lines up pretty well with the 100 million year group of stars. So we think that this star, and indeed the group, is about 100 to 150 million years old, which is great because that's after the disk migration time and kind of at the very early point when we might expect scattering. But it probably means that these planets migrated to the disk, not least because there are 2 of them. So scattering is a great way to get 1 planet in close to the star, but it's hard to get 2 planets to scatter in together. So most multi-planet systems with 2 or more planets on short orbital periods, we think that they migrated to the disk. The other way we determine the youth of stars is by using lithium. So lithium is a kind of a primordial element, hydrogen, helium, lithium. And so it's there available in these molecular clouds that form stars. So it's there sort of in the inventory of the star. But what's interesting about lithium is that it has quite a low burning point. It's about 2.5 to 3 million Kelvin. You can start to burn lithium, which is lower than the temperature you need to get to in the center of the star to start nuclear fusion. So you start burning up your lithium before you really get the nuclear fusion going. So once stars are born, they contract under the gravitational potential energy and they heat up. So as soon as they form, they start heating up. And so as they get hotter, they start burning lithium. And so you can use the amount of lithium that has been burnt as a way of diagnosing the age of the star. What we're seeing here is that depending on the temperature of the star, for young stars, 100 million years old here in Cyan, lithium is a large spread, but lithium is usually quite a lot of it. By 670 million years, the amount of lithium has gone down a lot, and here there are just null detections. And then for very old systems, it's about kind of 1 to 10 gigayear systems, the amount of lithium is very low indeed. Our system, we would expect it, because of the rotation period, to be lining up with the Cyan points. And indeed, it does, which is another indicator that this system is about 100 to 150 million years old. The other thing we want to do is to know whether this is an individual star. And so the way we do this is to take, we call it speckle imaging, so it's very high contrast imaging, where you kind of block out the central star in the center here, and then you take lots of very, very rapid exposures, boom, 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 one after another. And the idea is that you can do that faster than the atmosphere can change. And so you kind of mitigate the scintillation effect, which is what makes stars twinkle when you look through our atmosphere at the stars. And this gives us some indication of what is around the star, like very, very close to it. In this system, if we blow up the image here, and we look down here, I'm not sure if you can see it on the quality of the projection, but actually there's a very, very faint source here, about 0.6 arc seconds away, which at that distance it's about 70 parsecs away. So we think it's a likely binary star system, which is quite cool. It's quite fun. That's kind of gives an additional element to what might have been affecting the disk and the potential migration of these planets. But as I said, we think disk migration is the more favorable option. So now we're pretty sure that the star is young, pretty sure we've got planets, the transits there. A couple other things we want to do are to look at the radial velocities. This is the way that 51 PEG was found. So looking at the reflex motion of the planets on the star. So the star wobbles because of the gravitational pull of the planets as they go around. These planets, however, are sort of sub or mini Neptunes, not big gas giants like Jupiter. So that they weigh a lot less. So the pull that they have is a lot smaller. And that means that we should pretty much see a flat line here. And it'd be very difficult to determine the masses of these planets from radial velocities, at least the radial velocities that we have obtained so far, which is exactly as we expect, which is good. So pretty much a flat line. If these were varying over much larger amplitudes than what we expect, and that's probably a cause for concern. But so far, so good. Natural next question, are there any more planets in the system? We found 2. Did we miss any? Did our algorithm miss any? And the way we determine this is by injecting fake transits into the data. So we say, okay, let's inject a set of periodic transits with lots and lots of different periods and lots of different radii, and then we see which ones we can detect back. And so this is telling us how sensitive we are to different kinds of planets in the system at different orbital periods. So anywhere it's kind of yellow here, we have pretty much complete sensitivity, and then where it's dark green here, we miss pretty much everything. So we can be reasonably confident that there are no Neptune-sized or bigger planets out to about 30 days, but we really can't say all that much about any Earth-sized planets. So there could be more planets in the system, we just don't have the sensitivity to find them. Now, you remember some slides ago, I was showing you the radius against the orbital period of all the planets we've found so far. Showing you exactly the same thing again, just zooming in on an interesting part of the diagram. So here are your hot Jupiters, here are your mini Neptunes, and here are your super Earths. And so we can plot all of the young planets that we found. So these systems are old systems. And the idea is, do the young planets line up with the old systems? So the young planets fall here. It's quite an interesting thing that we see. So the youngest planets are colored in the yellow and green colors, and the older young planets are colored in the sort of darker green to blue. And we see that the youngest of the young planets actually sit in this region here, which is not very well populated by the older planetary systems. And as you move to older ages, to about 100 mega year up to about a giga year, we start falling into this. We find more planets in the same region of the diagram as we find for older systems. And this leads us to one of a couple different ideas. Either these planets are still cooling and they're contracting as they cool. So these planets, as they get a bit older, these very young ones, they will cool and contract down to somewhere within this population that we would expect for them. The other thing it could be is that the host star, because these planets are really close to their star, these have orbital periods, for about 10 days, it could be, the host star could be blowing off the atmosphere. This is called photoevaporation. And so one of the sort of key areas that are being worked on at the moment within the exoplanet field is this idea of what's causing the structure that we see in this part of the diagram. Now, by eye, it's pretty hard to see that there's any kind of structure. This looks a little bit like a blob. Very eagle-eyed among you might be able to see that along this kind of line, there seems to be a slight decrease in the density of points. So if we take a look at this region here, if we zoom in, and then let's repurpose our x-axis. Instead of the orbital period, let's use the light intensity. So this is now taking account of what kind of star you are. What's the host star? So if you have an orbital period of 10 days, it matters whether you're orbiting a really massive, very bright star or a much smaller, fainter star. So this is kind of correcting for the effect of the host star. This is now kind of plotting, instead of individual points, plotting contours of relative occurrence. So the dark red is where you have the highest occurrence of planets. And you go down to this lighter yellowy white, it's where you have the lowest occurrence of planets. So this region here is called the photoevaporation desert. This is where we don't think there should be any planets because the the UV and X-ray light is that high energy radiation from the host star we think would blow off the atmospheres or photoevaporate the atmospheres of these planets and remove the kind of gaseous envelope and push them down here into sort of just a bare rocky core. And you can kind of see this dearth of planets over here, and that's this bit here. You also probably notice that there's a bit of a bimodal distribution here. So more planets in this group, other planets here, and then between the two, there's not a huge amount. Now, if we, instead of plotting all of our systems, what if we just look at the best, most well-characterized systems that we have? If we do that, then what we see is that indeed there is actually what appears to be a genuine gap. So although these are colored in two different colors that kind of guides your eye and it's a little bit cheating, even if they weren't colored in blue and red, and we didn't have this line between the two, you'd probably still conclude that there was a lowering of the density here between the two groups. And one of the ideas that we have is that along this sort of trend here, planets will struggle to keep hold of their atmosphere. So if another way of showing this here is if we basically sort of squash all the planets along this direction, we can make a histogram that looks, oh, my apologies, over eager. We can make a histogram. So this, a nice peak here for all the planets that are in blue, a peak here for the planets that are in red, and we have a decrease in the gap between the two. And the idea is that planets that are sort of on the inner edge of this population here that have a gaseous envelope, these are kind of mini Neptunes, they can't keep hold of their atmosphere in the presence of the stellar irradiation. This is the UV and the X-ray high energy radiation. And so they actually lose their atmosphere and end up joining this population. So they jump across the gap. So on the one hand, you think, okay, if you're that close to the star, that's a pretty bad thing because the high energy radiation from the star is just going to remove the atmospheres that we might want to protect. And indeed, it's not clear whether these objects here, for example, still maintain an atmosphere or whether they are just a bare rocky core. So potentially being close to your star is bad. On the other hand, it could be that being close to the star is good and the high energy radiation from the star is good. So in the last thing I want to talk to you about is the potential for flares from low mass stars being important for potentially initiating and sustaining prebiotic chemical reactions on the surface of rocky planets. So there are three things that we think that life requires. You need information carrying molecules, DNA, RNA. You need molecules that promote and control reactions. So your proteins, and you need sort of membrane container-like molecules, these phospholipids, give you a nice barrier to the outside world and also allow energy exchange via ion gradients, etc. Now, one of the key questions that's arisen, if life needs these three things, which one came first? So it's kind of a chicken and the egg kind of question. Ideally, of course, you'd find a way to try and produce all three with some common form of chemistry at the same time. One of the ways which this has been proposed, actually including people involved in Cambridge at the LMB, is you can do this with essentially a hydrogen cyanide, which we think would be prevalent on the early Earth, and a certain amount of light, particularly at about 250 nanometers. This is in the UV part of the spectrum. If you don't have the requisite amount of light, then you end up following what's called the dark chemistry route. So you follow a different set of chemical reactions, which are a little bit less interesting. But if you have enough UV light, then you can follow a more interesting set of chemical reactions that actually end up generating RNA precursors, as well as interesting phospholipids and proteins eventually within the kind of full chemical network, a lot of which I will save you from showing. The key point is that you have what is called an abiogenesis source. It's kind of an energy requirement. It's the minimum energy you would need to deliver in the UV part of the spectrum to promote and sustain this set of chemical reactions, which could be one of the ways in which life could get started. It's an origin scenario. What's interesting on this plot, this is showing the temperature of the host star. This is the orbital period of planets. The planets that lie in the habitable zone of their stars, plotted in black and red here. So the habitable zone is defined as the region around a star where you could have a temperature on the surface of a rocky planet that would allow water to be in liquid state. So between 0 and 100 degrees. That's kind of loosely defined what the habitable zone is. And this follows a track. So for very low mass stars, you have to be quite close in to the star to be in the habitable zone, because the star is low mass, it's faint, it's not emitting that much light. So you have to be close to it to be in the right temperature range. And as you go out towards, here, this is the Earth, this is the temperature of the sun, 5,000 Kelvin, then be further away and still be in the habitable zone. Interestingly, the Earth, or the Earth-Sun system, satisfies both requirements. So the UV light from the sun, the early sun, is actually the right amount at the location of Earth to initiate and drive these prebiotic chemical reactions that we see here. For low mass stars, though, there's a disconnect between the habitable zone and the abiogenesis zone. This is kind of a temperature requirement, this is an energy requirement. So does that mean that any planets around low mass stars can't be habitable if this origin scenario is the right one? Or is there a way in which we can try and push down this abiogenesis zone and help out? And one of the ways in which we might be able to do that is via flares. So flares are these eruptions of high energy radiation, predominantly in the UV and X-ray. A couple of examples which are shown here. This is our sun taken by NASA's Solar Dynamics Observatory. This is an X-class flare emitted. This is taken in the extreme ultraviolet part of the spectrum. This is a high energy radiation. You can see a flare. This is the optical here. Nice bunch of star spots where the flare seems to originate from. And then in the UV, this is where the flare is brightest. So that's the key point, that flares generate a lot of UV radiation. And that's what we want to see. So the key point here, and this is kind of really credit to Paul Rimmer, who's here at Cambridge, who noted that the UV, amount of light in the UV part of the spectrum, so about kind of 250, 260 nanometers from the young sun, is actually similar to a low mass star, which is shown in black here. It's actually similar when that star flares. So as long as you have a low mass star that flares enough, you could have a similar amount of UV light generated in the habitable zone as the young sun did for Earth. And as I said, we now know where lots and lots of young stars are. So why don't we use test data to try and find these young stars and see whether they flare enough to corroborate or disprove this origin scenario. So this is a light curve of one of the young stars observed by TESS, and the data is colored by the probability of there being a flare. So black is very low probability of a flare. It's just the normal rotational modulation for star spots, and all the bright orange colored points are where the model that we're using thinks there are flares. So we can model each of these flares, determine their energies, and count up how many flares there are at different energies, and then we can see whether we get the right amount, just zooming in here, whether we have the right amount of energy for to satisfy this abiogenesis. So what we can create is what we call a cumulative flare frequency diagram, where we're counting up all the flares that have a certain energy. And the ideal is that this line would cross or get close to this line. So if this particular system, it doesn't look like it's enough, what about for all systems in general? There's some work being done by a master's student here, Sophia Kalamatiani, who I do some work with. She's been doing some great, really nice work mapping this out for different for stars of different ages. She's looking at one particular temperature range, but these are average tracks of stars with different ages, going from young with yellow to old dark blue, and then we're trying to see how close we can get to this abiogenesis zone requirement. The results are still preliminary, but the key takeaway at the moment is it seems as though, on average, young stars don't have enough flare frequency, flare energy frequently enough to drive the chemistry, but a small fraction of the stars could. So these are the average tracks that we see. But if only even 5% of stars satisfy this criterion, that's still many planetary systems that could satisfy this origin scenario. And then I will conclude. Interesting, this conclusion slide has not come up the way I intended. Okay, but anyway, we say that we looked at the how we viewed the solar system, and then we realized that although there might not be that much evidence of life in the solar system, at least now, that there are many exoplanetary systems that we're finding. And one of the key things we need to do, which will help us answer questions about the evolution of planetary systems, is to find young planets. And in addition to finding young planets, we can test some interesting origin scenarios for planets around low mass stars by looking at their flares and whether they can satisfy, initiate, and sustain the required prebiotic chemical reactions. With that, I will thank you for your time, and apologies if I overran slightly. So thanks very much.